A box with an open top is made from a square piece of cardboard, side length 12, of side length 12 centimeters, by cutting equal squares into the corner and folding up the sides. Draw the diagram of the box and label it with an L for the side length of the removed squares and H for the height. So I have a box here. What we're told is that this is 12. This is 12. Okay. And here, the side length we have is L, and this is H. Okay. So that gives us our box that we have in terms of when this is our net, which is basically the box folded apart. So what does this look like if it's not folded apart? Well, it looks like this. We've got our box. This is side length L, and this is H. And this is empty. Okay. Now, if we want to look at an expression for the box as a function of the side length with the square cut corners, what we have is we have that 12, the expression for the volume. Volume equals L squared times H, which is lovely. Now, here, my total length and total width is 12. So 12 equals L plus 2H, or H equals 6 minus L over 2. So if H equals 6 minus L over 2, then V equals 6L minus L over 2. Or, sorry, 6L cubed minus L squared over 2. There's something here I'm not. Oh, 6L squared minus L cubed over 2. And here we have our expression for the volume. And we had to use the height to create and replace our H using L. Now what we want to do is we want to find the length of the side length of the square cut that maximizes the volume. So we want to find the H that maximizes the volume. So here, when I have this expression, we need H and L are greater than or equal to 0. So I like to use this to create a bound. So L is less than or equal to 12. So L is in 0 to 12. And there's nothing stopping it from being 0 up to 12. That side length could be 0 length, or it could be up to total length of 12, in which there's no cut into the box. So now, because it's a closed interval, I can use the absolute extrema over a closed interval test, which means I need to figure out what my V prime is to find my critical values, and then compare it with the endpoints of 0 and 12. So if I look at V prime, it's 12L minus 3L squared over 2, which equals 3 over 2 8L minus L squared which equals 3/2, 3L/2, 8 minus L. And now from here, my critical values are L equals 0, or potential critical values, I should say, are L equals 0 and L equals 8. Creating a sign chart of 0 and 8, we have 3L/2 and 8 minus L, positive, positive, negative, negative, positive, positive. Creating a sign chart, we see that we're negative, positive, negative, so decreasing, increasing, decreasing. As f prime of x is greater than 0, just before, and f prime of x is less than 0, just after. The critical value x equals 8. There is a local max at x equals 8. Now here I'm diving straight into the first derivative test to show it's a local max. But remember, because it's a closed interval, I don't need to do any of this. Because it's a closed interval, I can simply look at a of 0, a of 8, and a of 12. And a of 0 is 0. A of 8, if we look at our original expression, is 6 times 64 minus 8 squared times 8/2, which equals 6 times 64 minus 4 times 64, which equals 2 times 64, which is 128. And now when we plug in, I guess it's V, we plug in V of 12, we get 0 as well. So we have a maximum. We have a maximum when L equals 8. Well, now I need to figure out what H equals. H equals 6 minus L/2, which equals 6 minus 8/2, which equals 6 minus 4, which equals 2. So the volume is maximized when the corners are cut 2 centimeters. In this question, we're looking at the general formula of the ellipse, and it's asking us to compute dy by dx, so it's implicit differentiation, and it gives us a point. So we're going to calculate the implicit derivative and plug it in. So here, 2x over a squared plus 2y over b squared times dy by dx equals 0. So 2y over b squared dy by dx equals minus 2x over a squared. Now cross multiplying gives me dy by dx equals x over y times a b squared over a squared. And we're going to plug in our points. So this equals 0.6 over b times b squared over 0.8 over a times a squared, which equals 0.6 b over 0.8 a. And we have our conclusion. Now we're going to look at the tangent line that passes through this point. And remember, the tangent line that passes through this point, y equals f of a plus f prime of b x minus a, or f prime at a. And remember, a in this case is 0.6 over b, and f of a in this case is 0.8 over a. So y equals 0.8 over a plus, and the derivative is 0.6b over 0.8 a times x minus 0.6 over b. And this is our general form for the equation of the tangent line, which looks a lot like our L of x. In fact, it is, the linearization is the tangent line about the point. And this leads us great into our linear approximation of the values. Linear approximation Lx is equal to f of a minus plus f prime of a x minus a. Now, here, when we're looking at a cubed root, we want a nice value. The nice value that we're going to use is a equals 8 is nice. Why? Because the cubed root of 8 equals 2. So f of x equals x to the 1/3. A equals 8. F of 8 equals 8 to the 1/3, which equals 2. Now f prime of x equals 1 over 3 x to the minus 2/3. And f prime of 8 equals 1 over 3, 1 over 8 to the 2/3, which equals 1 over 3 times 1 over 4, which equals 1 over 12. Combining this all together, we get L of x equals 2 plus 1 over 12 x minus 8. And this is, we're going to plug in x equals 7.96 for our approximation. So L of 7.96 equals 2 plus 1 over 12 times 7.96 minus 8. So this linear approximation of 7.96 is going to equal 2 plus 1 over 12 times 0.04 with a negative sign. So this equals 2 minus 0.01 over 3, which equals 2 minus 1 over 300, which equals 600 minus 1 over 300, which equals 599 over 300. And that is our linear approximation of 7.96.